Good evening, everyone. So welcome to the 8th problem solving session for the course Structural Analysis 1. I have turned on the recording. Let me share my screen. So the topics that we'll be looking at today is the method of consistent deformations, applied to beams and frames. And we'll also be looking at one specialization of the method of consistent deformation to multi-span continuous beams, which is called the three-moment theorem. So the recording has started and I hope the screen is visible. So we were looking at in the last session, we saw that for the analysis of statically indeterminate structures, we have two classes of methods. One is called the force method of analysis, where the redundant forces are treated as unknowns and the compatibility equations help in determining the unknown redundant forces or reactions. And we also have the other class of methods called displacement methods of analysis. In those, the displacements at various joints in the frame structure are treated as the primary unknowns, and equilibrium equations are used to solve for these unknowns. In the force method of analysis, we have already seen the method of consistent deformations applied to trusses in the last session. So in the last session, we considered various trusses subjected to different loadings, and we identified redundant internal and external forces. We came up with a primary structure, which is statically determinate and stable, and then determine the unknowns by enforcing the compatibility equations. Today, we'll be doing the same thing for beams and frames. So the concepts are exactly the same. What is different is only the application. So the degrees of freedom in a beam are slightly different. Apart from that, the overall concept is exactly the same. So when it comes to So let me quickly review how we are going to do it. Suppose we have a frame structure like this. We have a frame structure, which is. So this is a statically indeterminate beam. As usual, as with any forced method, the first step is always to determine the degree of static indeterminacy. So let us call it NS. So once we have determined the degree of static indeterminacy, the next step is to identify redundant forces or reactions. So in the context of beams, let me call both forces and moments as some generalized forces. So when we were looking at trusses, the internal forces are all only axial forces. But when we come to a beam, we can also have redundant moments. So we need to identify redundant forces and moments or reactions as well. So if you look at this structure, which is a fixed beam, the degree of static indeterminacy is in general 3. We have 3 equations of equilibrium and we have 3 unknowns. We have 6 unknowns, which is 6. The beam is statically indeterminate and it is externally indeterminate. Externally, we have 3 reactions here, 3 reactions here. So there are 6 unknowns and 3 equations of equilibrium. So what can we identify as the redundant forces? There are 2 options. One, we can consider it to be a simply supported beam with the moment on both sides and this reaction as n. So this is choice 1. We can also have another choice, which is we consider it as a cantilevered beam with all 3 forces on the other side as unknown. And there are so many of these choices. We can. So these are two common choices that are normally adopted. So once we have identified the redundant forces or reactions which are unknown before solving the problem, the next step is to draw the primary structure subjected to external loading. So suppose the primary structure, which is what is obtained after removing the redundant forces, and it should be, statically determinate and stable. It's a condition. So it holds in the case of beams as well. So this primary structure should be statically determinate and stable, and you determine the displacement variables, displacements or rotations, where at the point of action of the redundant forces. So if there is a redundant force here, consider C2. Suppose there is a horizontal force here. What is the action of that horizontal force? The horizontal force acts so that this point does not move horizontally. Similarly, the vertical force is acting such that this point is held in place. Both in the present, suppose there's a loading here. The horizontal force ensures that under the applied loading, this point does not move horizontally, and the vertical force stops it from moving vertically, and the rotation restrains this point, this small section of the beam from generating any slope. So determine the displacements and rotations in the primary structure due to the applied external loading. Let us call it D1L. So 1 corresponds to the first redundant force, 2 corresponds to the second redundant force, and so on. Then what is the next step? Now consider the primary structure subjected to the redundant forces. So since we are limiting ourselves to linear elastic analysis, we can use the principle of superposition. So if you have the primary structure subjected to a redundant force x1 like this, you can always, so let me call this x1, x2, and x3. You can always consider this as a scaled version. So you can consider, so whatever the bending moments, stresses, displacements, everything that is obtained is just multiplied by what is obtained when we apply a unit load at the same point. So what will be the displacement of this point due to the applied unit load here? Those we have a special term called the flexibility coefficients. We have already seen that. So F11 is what? F11 is the displacement at the point 1 due to a load applied at the point 1. So in this case, what will be the displacement of this point due to the applied load x1? It will be nothing but x1 F11. But this point will also move due to the action of x2 in the one direction. So you also have plus x2 F12 and so on. You have all these things. Finally, our task is to enforce the. So this is basically determine the flexibility coefficients. And final step is to enforce the compatibility, which is the consistency of deformation. Enforce compatibility conditions. Right. So in our case, what are the compatibility conditions? We want the point to be fixed in place under the action of all the applied loadings and the redundant forces. So we have, due to the first redundant force at the first point, we have a displacement of x11 f1, sorry, x1 f11 plus x2 f12 and so on, plus d1L should be equal to 0. Similarly, we have x1. Due to x1, the load acting due to the load x1, there is also a displacement along the 2 degree of freedom. So we have x1 f21 plus x2 f22 plus d2L is equal to 0. And so on. We have a set of n by n. If ns is the degree of static indeterminacy, we get a matrix of size ns by ns with ns number of unknowns that cannot be determined by static equilibrium alone. So this will be f11, f12, and so on. Here we have x1 and so on is equal to what are the displacements due to the applied loading, which is d1L and so on. So this is ns. So we solve this system of equations and determine the unknowns x1, x2, x3, and yeah.
Sir.
Yes.
Yes. Could you please pull the page up so that I can note down the step 4 and step?
Sure. Yes.
Or I could just take a snapshot.
Yeah, sure. I'm. You can take a screenshot here. Then I'll go down. You can take a screenshot there also.
Yeah, I have taken till step 3.
Okay.
Now step 4 to step 1 minute.
Yeah.
Yeah, taken. Yes, sir.
Okay. 1 minute. There is some. It's not detecting my. Yeah. So these are the basic steps. Now the only part that is remaining is how to determine. So these are the this is the overall procedure. Now the next thing that is remaining is how to determine these.
How to determine the
Yeah. So how to determine the flexibility coefficients and the displacement due to applied loading. So this is very simple. We have seen it multiple times. We have so many methods to do it. So you can use any method. You can use the conjugate beam method or the moment area method, but the easiest is unit load method. So we'll use unit load method to determine these coefficients. Why? The reason is we are subjecting it to a unit load and treating this as unknown. So when we use the unit load method, we'll get in one step the flexibility coefficient. So if you remember the unit load method, what do? We apply a unit load. And what is the displacement due to the unit load? Due to the so we have the real forces and the virtual forces. We apply a unit virtual force. And let us assume that the real forces are already applied. So we apply a unit virtual force and then we apply the real forces. So once we apply the real forces, the structure begins to deform. So in that process, the virtual force will do some work on the real displacements d1L. And what should be that equal to? So this is the external work done. Work done by the external virtual force on the real external displacement should be equal to the work done by the internal virtual force. So what is the internal virtual force? Due to a applied unit virtual load, let me call moments mi, small m1 is generated. Okay. So if mi is generated, that is at the ith. So corresponding to ith redundant force, I'm applying a unit load, and corresponding to that unit load, moments small mi are internally generated. Now these internal moments will do work on the real internal displacements, which are m by ei. So this is something like a rotation. Sorry, this is a curvature. M by ei into dx will be a small rotation. So integrated over the length of the beam. So this is how you determine the displacements due to the applied real loading. So this is again virtual internal forces. These are the real internal displacements. Now, how to determine the flexibility coefficients? So to determine the flexibility coefficients, what are flexibility coefficients? It is the displacement at a certain point due to a load applied somewhere else. So where we want to determine the displacements, you call that point as, say, I, and where you want to where the load is applied, take that point as J. So because of a unit load acting at the point J, the displacement at I will be nothing but Fij. And how is it? Now treat one of them. So treat this as the virtual force applied at point I. You have some structure, you have a point I, you have a point J, you have a force, a real force acting at point J, which is a unit load, and you want to find the displacements at this point. So apply a virtual force at this point, a virtual unit force at this point. So this is this Fij is equal to, use the same formula, Mi mj by ei dx. So this is the formula for flexibility coefficients, and this is how you determine the uh, displacement due to external loading. So this summarizes the method. So we can get started with the problems. Before that, there's also this extension to add a page. So this is one method. So if this method, unit load method, works for frames, it works for it is a general method. It works for any structure because it's based on the powerful principle of virtual work. The other method is Clapeyron's theorem of three moments. Clapeyron's theorem of three moments. So this is very useful when we have, this is a simplification of the method of consistent deformations applied to continuous beams. So suppose we have a multi-span continuous beam like this. Something like this. So if you had seen the first lecture of this week by Sir, he would have derived the theorem of three moments from the method of consistent deformations by considering an intermediate span A, B, C. So what do they do? This structure is statically indeterminate to the third degree. So I have unknown reactions here, here, and here. But instead of treating the vertical reactions as redundant forces, he treats the moment at these joints as redundant moments. So the moments at joints A, B, C are redundant. Now, how does that help? It helps because once you release the moments, you have a series of. So once in order to release a moment, you put internal hinges, right? Sorry. So here you have initially there is some unknown moment that is acting here, MA, MB, MC. When these are treated as redundants, we need to obtain a primary structure without the redundance. Of course, there are some loadings. So the primary structure we obtain will be like this. Now this is statically determinate because it is a series of simply supported beams. So this will deform like this, this will deform like this, this will deform like this, this will deform like this. Now what is the compatibility condition? So if it is a simply supported beam, if there is an internal hinge, the rotation of this beam to the left, the rotation of the beam at this point to the left will be different from, so theta of A to the left will not be equal to theta A to the right because there's an internal hinge, the slopes can be discontinuous and the moment transmitted is zero. So what we do? So if this is in the primary structure, to enforce compatibility, we need to make this equal. So we find what moment should be applied at this point. So what moments ME, MB, MC will ensure that the rotations are compatible. That is the idea. So again, they use the principle of superposition. They find the rotations due to the applied loading plus those that are caused by the redundant moments. So the good thing is, if you take this span, if you apply this moment alone, this moment will not, if you in the primary structure, once you apply the first redundant moment, that moment will have no effect on the spans that are away from this. So the system of equations we have will at a time will contain only 3 moments. So that is, we have something like theta a bar, suppose it is due to the applied loading, plus theta AB should be equal to theta A double bar, say have theta A bar due to the applied loading plus theta AB, which is caused by the moments, should be equal to the what is obtained on the right hand side. So theta A double bar or theta A bar prime, or let me call it left and right ones. This is left plus theta BA. So this is the idea, the rough idea. Once you do this, so when you analyze each of the simply supported beams with some method, you can use the conjugate beam method or the moment area theorem, any method, or even the unit load method. You can use any of it. At the end, the expression that we get for the 3 moment for solving the compatibility equation that we get finally, let me write it down so that we can use it for the problems. It is so if you have 3 joints like this, and as I said, at a time, we need to consider only 3 moments. We don't need, we will not be getting a full system. We'll get a full coupled system, but each compatibility equation will involve only 3 moments at a time. So that is that will offer computational advantage in solving this problem when the problem size is very big. So the 3 moment equation is as follows. That is MA LAB. LAB is the length of this span AB. So this is LAB by EAB IAB plus 2MB LAB by EAB IAB plus LBC by EBC IBC plus MC by EBC IBC. This is equal to -6 times AAB. I'll say what AAB is and XAB by LAB, EAB, IAB plus ABC, XBC by LBC, EBC, IBC. Here, AAB is nothing but the area under the bending moment diagram of the span AB. And XAB is nothing but the centroid of the area under the BMD. That's it. Similarly, ABC is area under the bending moment diagram of the span BC. And XBC is nothing but the centroid of this area. Area. So that's it. So this is the 3 moment equation. Now, in the presence of, and how do you determine the area? So area has the same sign as the bending moment diagram, and XAV is always taken from the distal support. So XAV is taken from the distal support. Okay, don't worry about it. That's not so important. Now, if the good thing about this is, in case one of these supports is settling, as I said in my one of the introductory sessions on statically indeterminate structures, suppose this support settles by some delta B, this support settles by some delta A, and this support settles by some delta C. If there is support settlement, then these equations get modified as, because the support settlement will induce certain additional reactions, and those reactions will cause extra bending moments and slope in this structure. So the slope that is caused, the rotation that is caused by support settlement should also be incorporated into the compatibility conditions. So when we have support settlement, there is an additional rotation at the joints, so that should also get added to the compatibility conditions. Now that gets added as 6 times delta P minus delta A by LAB. So you can see that delta B minus delta A is nothing but the relative displacement of B with respect to A divided by the length AB will be a rotation, which is caused by support settlement, plus delta B minus delta C by LBC. So this is the complete expression for the three moment theorem when there is support settlement and also applied loading. So this is an important expression which we'll be using towards the end of today's session. And deltas are positive downwards. So supports usually settle, they don't go up. Delta is positive downwards. And M's, as usual, they are, we know, right? This is the positive sign convention. So that's it. We can quickly get into the problems for today. We have about 15 problems, but it's a set of three problems related. Okay, so shown below is a statically indeterminate beam. Obviously, this is a statically indeterminate beam. And let us, so what is the first step? The first step is to determine the degree of static indeterminacy. You can easily see that there are 1, 2, 3, 4, 5, 5 reactions, and we have 3 equations of equilibrium. So there are, so degree of static indeterminacy is 2. And what else do we have? We have the redundant forces By and Cy. So that is what they ask. Let the redundants be By and Cy. Let us call By as the unknown x1 and Cy as the unknown x2. So we have identified the redundants. Once we have identified the redundants, what we should do? We should draw the primary structure. So before that, it always helps if we guess the deform configuration, whether it's a statically determinate beam or an indeterminate beam. So intuitively, so this is how the beam is loaded, and these two loads are equal. You can see that the structure is symmetric about the center line. So it is a symmetry axis. So how do we expect the structure to deform? We expect it to deform this way. And what do we actually expect after solving the problem? We expect that By is equal to Cy because the structure is symmetric. So this is a helpful tip. Always draw the deformed shape and reduce whatever you can before we solve the actual statically indeterminate beam. Now, what is the third? So, what is the primary structure? The primary structure is what we get after releasing the restraints caused by By and C. So, it is just this. So, this is the primary structure subjected to the applied loads. How does it deform? It deforms like this. Now, what is the displacement at this point due to the applied loading? So, this is nothing but d1L. This is d2L. That's it. This is primary structure. Let me call it P. We also have the primary structure subjected to the redundant forces. So let me apply the redundant force here. I can apply a unit load, and whatever displacement I get, I can multiply by x1. So let me call this structure as R1 to denote redundant force 1. And we have the structure R2, which is redundant force 2. So this, say, deform something like this. This will deform something like this. So this is nothing but F11. And what is the displacement here? It is F21. Here, what do we have? This is F12, and this is nothing but F22. So this is multiplied by X2. So solving for this is step 3. So step 3 is to determine actually step 3 is the primary structure. We have done it. And step 4 is to get the flexibility coefficients Fij and the displacements DIL. What is the last step? The last step is to determine the unknowns x1, x2 by solving the system of equations F11, F12, F21, F22, x1, x2 is equal to d1L, d2L. So this is what we'll be doing in today for the first 12 questions of, sorry, 9 questions of today. So, so this first problem is to determine d1L and d2L. So he calls it dl1 and dl2. It is very simple. So how do we do it? Let us consider this structure. Now, before that, is the primary structure with the applied loading symmetric? Yes. So this structure is also symmetric about this axis. So what do we expect? We expect d1L should be equal to d2L. So if you look at the options, there is this option C, which is having d1L and d2L not equal. So obviously this is a wrong answer. So that is the idea. The drawing the deformed shape initially will help us identify certain features of the solution, and will also help us to check our answers after we solve the problem. So let us solve the problem. What is the bending moment diagram for this? Right now, since you're all very much practiced in this aspect, it is nothing but, so we have two forces, 240, 240 here. So the reactions will also be 240 and 240. So bending moment diagram, the real bending moment diagram will be, so this is a reaction 240, it acts at 6 meters. So here it is linear, here also it is linear. And as we move away, what is the bending moment? So there is no shear force, the shear force is 0, so the bending, it has to be flat. What is the magnitude? It is 240 into 6, which is 1440. So the magnitude is, or let me draw it. The convention is I'm going out of. So let me take up positive upwards. Kilonewton meter. And what is the virtual bending moment diagram? So because of a unit load that is applied here, we know that the reaction that comes here will be this distance, which is 24 by 36. So you have a reaction of 2 by 3 here, and it acts at a distance of 1 by 3. So the bending moment at this point will be 2 by 3 times 1 by 3, which is 2 by 9. Let me check. You have the reaction will be 2 by 3, and it acts at uh, 12. So it is 2 by 3 times 12, which is nothing but 8 kilonewton meter. So here what we have is 8 kilonewtons meter. And you have the other redundant structure, just like this. So it helps to find these values. So this is nothing but 4 kilonewton meter. And this here also. So you see this is 12 and it acts half the distance. So this is also 4 kilonewtons. And all of them are positive. So that's it. So what is D1L? D1L is nothing but integral of. So 1 acting on D1L is integral 0 to L. The virtual bending moment diagram M1. So let me name this. This is M of x. This is real bending moment. This is the virtual bending moment due to the applied unit load at point 1, and this is the virtual bending moment due to the applied unit load at point 2. So the work done by the virtual unit force on the real displacement is equal to the internal work done by the internal virtual forces on the real internal displacements m by ei dx. So how do we do it? We need to split it because the function is discontinuous, not discontinuous. The slope is discontinuous. The function has different definitions in different segments. We need to split and split the integral into many parts. So how to do it? So this is nothing but, so this is 6 meters. This is 12 meters. So what we have is this is integral 0 to 6. So let me use x1 for. So let me divide it into 4 parts. This is part 1. This is part 2. This is part 3. And this is part 4. So let me use the coordinate x1 here, x2 here, x3 here, and x4 starting from this side. So that is the idea. So this integration, you can do it easily. We have already done it many times. So it is nothing but what is M1? M1 is 2 by 3 x1 acting on the real bending moment. What is the real bending moment? It is 240 x by EI into dx plus. Now consider region 2. So I have an origin here. So this is x1 going from 0 to 6. So here it is x2 going from 0 to 6 again. Right? The total distance from the left is 12 meters. We have already covered up to 6. So it is again 0 to 6. x2 going from 0 to 6. What is the function here? Virtual bending moment function. It starts at 4 and goes to 8. So it's nothing but 4 plus 2 by 3 x2 into the real bending moment is a constant at the region. So it is nothing but 1440 by EI dx2. And what is in region 3? So region 3, so let me color it in a different. Right, let me. So this is region 1. Up to this is region 3. And this is region 2 and this is region 4. That's the idea. So if you see region 2 extends from, so if you have a global X, so region 2 extends from 6 to 12. Region 3 extends from 12 to 24 minus 6. Sorry, 36 minus 6, which is 30. So 12 to 30 is 18. So x3 goes from 0 to 18. And there you have the expression for the bending moment as what it is. It is decreasing. It is starting at a value x, 8, and it is decreasing with a slope of 1 and 3. So it is 8 minus x3 by 3. What is the real bending moment? It is again a constant, 1440 by EI dx3 plus integral x4. Note that x4 is starting from the right hand side. So it starts at 0 and ends at 6. So x4 going from 0 to 6. The virtual bending moment is x4 by 3. And the real bending moment is nothing but 240 x4. So you can evaluate these integrals. It is a straightforward exercise. So what you get will be one by EI into, you get something like 160 by 3 into 6 cube plus 4 into 1440 into 6 plus 480 into 6 square plus 8 into 1440 to 18 minus 240 into 18 square plus 80 by 3 to 6. So this expression evaluates to 198,720 by EI. As I said, since the primary structure is symmetric, this should also be equal to D2L. We can also check this exactly because this is symmetric. If you do the integrations in the same way, starting from the right hand side, you get exactly the same expression. So what is the answer? The answer is option B, 198,720. Now let's move on to the next part. What is the next part? Next part is to determine the flexibility coefficients. So for that, we need only these two bending moments. Let me carry that forward to the next page. copy and page 2. Yes. So this is what we have. Now what is F11? So F11 is nothing but integral x goes from 0 to L, M1 acting on M2 by EL. M1. So again, I can split this into two integrals. So, or rather, yeah, two integrals from 0 to this is one region. This is the other region. So I can take it as a sum of integrals from 0. So x1 going from 0 to 12. M1 is what? It is nothing but 2 by 3 x1. And M2 is what? It is. So we are looking at F11. So M1 is again 2 by 3 x1. So whole square. Again, we have a 1 by E dx1 plus x2 going from 0 to 24. What is the function here? Now let me take x1 starting from this side and x2 starting from this side. So here the function is x2 by 3. The whole square 1 by EI dx2. So this is a very simple integration. You can perform it and what you get will be 768 by EI. Now what is F12? So to determine F12, you need to consider three regions. So that is, let me call this as region 1. We call this as region 2. And let me call this as region 3. So what is F12? F12 is nothing but integral. In region 1, x1 goes from 0 to 12. What is m1 of x? 2x by 3. What is m2 of x? It is x by 3. Let's then again 1 by EI dx1. In region 2, what is the difference with in region 2? What is, so if you see region 2, it is the integral is the same, only that m1 and m1 is m2 and m2 is m1. So in region 1, what we had for m1, you have in region 2 for m2. So in region 2, you have x2 going from 0 to 12, x2 by 3, 2x2 by 3 by EI dx2. And what do we have in region 3? We have 0 to 12, x3 going from 0 to 12. One of the functions, say the first function, so this first function is decreasing from 8 to 4. So m1 is 8 minus x3 by 3 and m2 is 4 plus. So all of these are quadratic functions. You can directly integrate them. And the answer that we get will be 672 by EI. So the flexibility matrix is 1 by EI. What did we get here? It is 768. Now what is F22? So note that F22 should be the same as F11 because why is that so? Because the what is F22? So F11 is integral m1 square by EI and F22 is integral m2 square by EI. which is the area under the square of the bending moment diagram. But note that the areas will be the same because it is just this bending moment diagram flipped about the mid-axis. So by flipping, the area does not change. So F1 is the same as F22. So it is 768, 672, 672, 768. Which option corresponds to that? It is option A. So we have 768, 672, 768. Now let's go to the next question. So the last and final step is to enforce the compatibility conditions. So how do we do that? It is so just a minute. Let me. There's a small correction here. So these, if you apply a vertical force, the reaction will be downwards, and these are actually in the other direction. So these are, it doesn't affect our answers, but just to be correct, these are actually negative. Just make this small correction. So these are actually negative, which means D1L will be negative. That's it. These two moments are flipping their signs. So this is negative. There's no issue with the flexibility coefficients because they're either the squares or negative multiplying by negative. So they are all positive. So that's why we have the deflection downwards, right? So that is obvious. These are negative. So when we go to the third problem, what is the system of equations that we have right now? It is 768, 672, 672, 768, and by EI acting on x1, x2. So much force here. These are the flexibilities. When this force acts on this, we get some displacements. And that plus D1L. So what is D1L? D1L is minus 197, 198,720. D2L is also minus 198,720. This is equal to 0. So this is a 2x2 system. You can easily solve it using a scientific calculator. Solving it, the answers that you get is x1 is equal to 138 kilonewtons, and it is the same as x2 as we expected. So both are positive. So the reaction acts upwards. So it corresponds to option D. Let us go to the next question. So here we have a fixed beam subjected to vertical loads only. So note that we only have vertical forces. And if the beam is initially unstretched or there are no temperature effects, the horizontal reactions are 0. So if the horizontal reactions are 0, they do not really account for unknowns. So the number of unknowns we have are only the shear force, bending moment here, and the shear force and bending moment here. So there are 4 reactions and 2 equilibrium equations, because one we have already used while looking at the horizontal forces. We have only 2 equilibrium equations, which is the sum of vertical forces is 0 and the moments about any point is 0. So the degree of static indeterminacy for this problem is 2. And they have asked us to consider the reactions Cy and Mc as the redundants. So the first redundant is Cy and the other redundant is Mc, the moment at the point C. So what is our primary structure? Our primary structure is a cantilever beam which is subjected to the applied loading and the redundancy. So we can use the principle of superposition and decompose it into a unit load. What is this? This is 100 kilonewtons. This is 10 kilonewton per meter. Here you have a unit load. And this redundant structure is scaled, all the forces are scaled by x1. Plus, you have the other redundant force, 1 kilonewton meter. This is scaled by x2. So let us determine what is D1L. What is D1L when subjected to this? The displacement we obtained is D1L. And what is D2L? Note that D2L is also at the same point, but corresponds to a different degree of freedom. So the slope at this point is like this. So this angle is nothing but D2L. So the degree of freedom 2, the value of the degree of freedom 2 due to the applied external loading. So let us solve for this. Now, what is the bending moment diagram for this capital M of X? Very simple. It's a cantilever beam. So first consider the segment BC. In BC, there is no reaction in the primary structure because you have released it. So what you have is a quadratic variation of the bending moment. And beyond that, what do you have? Beyond that, you have a constant shear force in the beam. So it is straight. So what is the value here? The value it takes here is 10 minus 10 into 10 square by 2. So it is minus 500 kilonewton meter. And then there is a discontinuity here because of the concentrated force. So let us find. So beyond this, it will be linear because it is free of any forces. You have only point loads. So from here, with the same slope, it continues up to a point. Or let me decrease. So up to this, it is quadratic. Beyond it, it is linear. Beyond this, it is linear. And beyond that, it is. So what is the value here? It is minus 500 kilometer meters. What is the value here? So the resultant force due to this distributed loading is 100 kilonewtons. It acts at the middle of this distribution, which is 5 meters. And we have at a distance of 5 plus 5, which is 10 meters. So here it is taking a value of 1000 kilometer meter, where the point load 100 kilonewtons is applied. Beyond that, what do we have? So at the support, we have the moment due to this, which is 100 acting at 5, which is 500, plus you have 100 acting at 1500. So sorry, you have 100 acting at 5, which is 500, plus you have 100 acting at 15 meters, which is 1500. So that causes 1500 plus 500, the moment of 2000 in the support. So again, it is linear because there is no distributed load. Here it is minus 2000 kilometer meters. And everywhere it is negative because it is hogging. The beam bends in this. Now let us consider the virtual bending moment diagrams. Because of a unit load applied in the upward direction at the tip of the cantilever, we know it is just linear. What is the value? The length of the beam is 20 meters. So 1 kilonewton applied at 20 meters is 20 kilonewtons. Positive. And then what is the virtual bending moment diagram due to the applied moment? It is under pure bending, so it is. Now let us solve the problem. What is d1l? d1l is integral 0 to L. So let's take the global coordinate x. And in this region, or rather, in every case, since it is a cantilever, it helps to have the coordinate system's origin at the right hand side. So let us take it as x. And here it is x1, here it is x2, here it is x3. So we'll split the integral into 3. So d1l is integral 0 to L m1 m by ei dx, which is nothing but integral 0 to. So the first region stretches from 0 to 10 meters. So 0 to 10. What is the virtual bending moment diagram? It is simply x. What is the real bending moment diagram? It is minus 5 x square. Yeah, minus 5 x square. You have the EI. Plus, what do you have in region 2? So region 2 extends from 0 to 5. And the real bending moment diagram is linear. What is the linear function that we have? So it is the linear function is. Oh, sorry, first the virtual. So virtual, what do we have? So at this point, since it is the middle, it takes a value of 10 kilonewtons meter. Here it takes a value of 15 kilonewtons meter. You can also extend it further down. So here it is just 10 plus x into minus 500 minus 100x dx plus integral. So we have covered region 2. Now let us see region 3. So this is x1. No, this is x. This is x1. This is x2. This is region 3. Again goes from 0 to 5. 15 plus x3. What is the real bending moment? It is minus 1000 minus 200x. You can substitute the values and check it satisfies. And that is divided by EI everywhere. So this can be easily integrated and the value that you get will be. So you can try it out. The value that you get will be minus 193750 by EI. What is D2L? D2L is integral 0 to L m2 of x m of x by EI dx. So even to evaluate, so d m2 of x is a constant, which is 1 kilonewton meter. So what we get is nearly the area of the curve under area under the bending moment diagram here. So it is nothing but integral 0 to 10. m2 of x is just 1 acting, and this is minus 5x1 squared by EI dx1 plus integral 0 to 5 1. And here what do we have? Minus 500 minus 100x2 by EI dx2 plus integral 0 to 5, 1 minus 1000 minus 200 x3 by ei dx3. If you evaluate these integrals, the answer that you get is, it's easy, it's a simple mathematical exercise. You can evaluate and find the answer as 12916.67 by ei with a negative sign. So the negative sign indicates that these points actually move downwards as the loads are applied, which is consistent with our physical intuition. So the correct answer is option D, where we have 193750 and 12916. So as in the last problem, we will require these virtual bending moment diagrams for determining the flexibility coefficients. Let us take it to the next page. So the next problem asks us to find out the flexibility coefficients. So, yes. So how do we determine the flexibility coefficients? We have that f11 is nothing but integral 0 to L m1 of x dx by di. So we don't need to split it anymore because they are continuous. The bending moment diagrams are continuous. It has the same definition everywhere. So f11 is nothing but x going from 0 to 20. m1 of x is x. m1 of x is x. So x squared by di. It's nothing but. So x squared will become x cubed by 3. So it's 20 cubed by 3. This is 8000 by 3ei. It's nothing but 2667.67 by ei. What is f22? That is even simpler. 0 to L m2 of x, which is 1 into 1 by ei dx. Nothing but 20 by 3 ei. Not 3 ei, 20 by ei. So we get x goes from, so it's L by ei and L is 20, so it's 20 by ei. What is f12? f12 is also simple. You have 1. Just a minute. This is not x, this is multiplication. One x by ei dx 0 to 20. So it is nothing but x squared by 2. So x is 20, 20 square is 400, 400 by 2 is 200. So what is the flexibility matrix that we get? It is 1 by ei. So the flexibility matrix is 1 by ei 2667.67 200 200 20. So which option does it correspond to? It is option B. Let's go to the next problem. So the last step is, as usual, to find out the unknown reactions. So what is the system that we get? We get 2667.67 200 200 20 acting due to x unknowns are x1 and x2 plus minus 193750 minus 12916.67 and everywhere we have 1 by ei is equal to 0. So since ei is constant, we don't need to worry much about it. So this is a 2 by 2 system. If you solve it using your scientific calculator, the unknowns are 96.87 kilonewtons, which is acting upwards since it is positive, and x2 is minus 322.92 kilonewtons. So the minus sign signifies that it is acting counterclockwise. We assume clockwise. We assume counterclockwise. So since we get a minus sign, it means it is acting clockwise. So the correct answer is option A. 96.87 kilometers upwards and 322.91 kilometers downwards. Go to the next problem. So we have seen beams, and now what we have is a frame structure. But the concepts are exactly the same. So we are given a statically indeterminate beam. As usual, the first step is to determine the degree of static indeterminacy. How many unknown reactions we have? We have 3 and 1. So we have 4 unknown reactions and 3 equations of equilibrium. So it is just 1. So finally, we'll just get a scalar equation to solve for. And what is the unknown? They have asked us to take the redundant. They have asked us to take the redundant force. Wait a minute. So they've asked us to consider Cy as the redundant force. So the primary, so the primary structure is something like this. With the applied loading. So how does it deform? It deforms something like this. Goes like this. Plus, so this is the primary structure subjected to the applied external loading. Plus the primary structure subjected to the redundant unit force here. So this structure can be the forces on this, forces, displacement, stresses, everything can be multiplied by x1, which is nothing. It's nothing but our Cy. So under an applied force, this deforms like this. Goes like this. Now, what is the compatibility condition? So compatibility condition is F11 x1 plus d1l. So this displacement is F11 x1 and this displacement is d1l. Compatibility condition is this because there is a restraint there. So given this, now how are we going to solve the problem? So the only difference is the energy, right? So how do you do? So let's determine d1l first. So a unit load is acting at a virtual unit load is acting on the real displacement d1l. But what is it equal to? It is equal to two things. So consider this member x1, consider this member x2. That's all. So it's integral 0 to 6 m1 m by ei dx plus integral 0 to 9 m1 m by ei dx2. That's all. Now let us determine the bending moment diagrams for this. For the primary structure, what does it look like? You start from the bottom. So this is kind of cantilever. So here you'll have a quadratic distribution. Or even before that, determine the reactions, right? So will there be any vertical reaction? No, there won't be any vertical reaction. There's a horizontal reaction of how much? The horizontal reaction is equal to 4 into 6, which is 24. And what will be the moment? The moment will be, so this force, the total force is 24 acting through the midpoint. So the moment will be 24 separated by 72. So the applied moment is clockwise. So the resisting moment will be counterclockwise. There's no vertical force. Now, if you draw the bending moment diagram for this structure, it is something like this. So here it increases. in a quadratic fashion. The final value is what? 4 into 6 square by 2. So 4 into 36 by 2. So 4 into 18 is minus 72 kilonewton meter. And this doesn't have any shear force, so it has a constant bending moment distribution of. So both are negative. What is the virtual bending moment diagram? So in the virtual diagram, you have an upward force of 1 kilonewton. And which means the reaction will be opposite. You will have a reaction of 1 kilonewton here. There will be no horizontal force. And what will be the bending moment? So the applied forces cause a moment of 1 counterclockwise. This will be clockwise. Where does it act? One acting at 9 meters. So it is 9 kilonewton meters. And this member is not subjected to any bending because there's no shear force and there's no bending moment. So this is just 0. And here it increases from 0 to 9. It is positive. Now let us find out what is D1L. So D1L is, since this member is having 0, the first integral is, so since M1 is 0, this first integral does not contribute. So this is 0. So this does not contribute. So the only contribution comes from this. And that is also very simple. What is it? This integral 0 to 9. The virtual bending moment is nothing but x, x2. So unit load acting at x2 distance, it is just x2. What is the real bending moment? Minus 72 by EI dx2. It can be easily evaluated. It is 30, so we'll get 36 x2 square, and that is nothing but 36 into 9 square. So 36 into 9 square is 2916 by EI. And the minus sign indicates that it is acting downwards. So the displacement D1L is downwards. So the correct answer is 2916 by EI. C. Now let's determine the flexibility coefficients. That is also very simple. So let me carry forward this diagram, the virtual bending moment diagram. So what is F11? F11 is nothing but integral. We have 0 to 6, it is nothing. So only this one contributes. So let me take this as x. So 0, x going from 0 to 9. X into x by EI dx. So x cubed by 3 is 243. 9 cubed by 3. So 81 3s are 243 by EI. This is option C. What is the last step? So the last step is to solve for this. So D1L plus F11 x1 is equal to 0. F11 is 243 by EI. D1L is 2916 by EI. And there's a minus sign here. So what is x2, which is the unknown reaction Cy, is by x2. So this is just x1, x1. It's 2916 by 243, which is 12 kilonewtons. And since it is positive, it is upwards. So that's the right answer. So this completes whatever this completes the set of problems that require the method of consistent deformations. The next problem we'll look at the theorem of three moments. So consider this beam. There are no external loads applied to this beam. The support at B sinks by 5 mm. So let us write down the problem parameters. So we have, what is LAB? LAB is 4.5. LBC is 3.75 meters. LCD is 3.75 meters. And IAB is I. IBC is I. ICD is 2I. And E is just E for all the spans. In addition, we have a support settlement of delta B is equal to 5 mm and delta C is equal to 10 mm. So since everything is in meters, we have to solve it in consistent units. So if everything is in meters, this will be 0.005. So that's it. Let us now apply the three moment theorem. What does it say? They're asking us to find. So ultimately, the goal of this problem is to determine the unknown reactions By and Cy. So the first step towards that is to write the three moment equation for this span. As I said, we'll have only three unknowns in a given equation. So first consider this span, then we can consider this span. So we have two unknowns, which is By and Bc, By and Cy. And we have two equations. So one is a three moment equation for the span ABC, and the other is a three moment equation for the span BCD. So what is the three moment equation? Let me bring it from the first introductory. So this one, right? Clapeyron's theorem of three moments. So this is what we have. And reduce the size. So we can write down based on the available data. What is MA? MA is 0 and MD is also 0 because they are hinged. So what will be the first term? It will be 2 MB into what is LAB? LAB is 4.5 by EAB is just E, IAB is I, plus what is LBC? LBC is 3.75 by EI plus MC. LBC. What is the span? LBC. LBC is 3.75 by EI is equal to, there is no applied loading. So the area of the bending moment diagram is 0. Here also it is 0. So these do not contribute, but we have a support settlement. What is that? So that is equal to 6 into what is delta B? Delta B is 5 and delta A is 0. So delta B minus delta A is 5 by LAB is 4.5. Plus what is delta B minus delta C? So delta B is 5. Delta C is 10 by what is the LBC is 3.75. So it is very simple. 4.5 plus 3.75 is 8.25. 8.25 into 2 is 16.5. And 16.5 and EI you can take it to the other side. So what you get is 16.5. And this one is multiplied by 10 power minus 3. Because this is an mm, we have converted it to meters, so we have this. So I have 16.5 MB plus 3.75 MC is equal to 6 EI into 0.005 into 1 by 4.5 minus 1 by 3.75. So EI is given as 80,000 kilonewton meter square. So it is 6 into 80,000 into 0.005 into 1 by 4.5 is 1 by 3.75. So what is the value that we get? This is, it is just a simple calculation. What we get is minus 106.67 kilonewton meters. So this is the moment, 3-moment equation for this span. So that is this. So I can see it matches with option D, 16.5, 3.75 minus 106.6. Let's go to the next part of the same question. So now we need to apply the same thing to span BCD. How do we do that? So let me bring, or rather I'll bring the question here. So this is the data that I require. I can bring this there. So So now we need to write the 3-moment equation for the span BCD. Right? So what is it? This blue color. MB LB by BCD, right? MB LB by EBC IBC plus 2MC LBC by EBC IBC plus LCD by ECD ICD plus MD LCD by ECD ICD is equal to, there is a term coming from the distributed loading that is 0. There is a term coming from the span loading. Since there's no load, it is 0 plus 6 into delta CB, right? So like delta C minus delta B by LBC plus delta C minus delta D by LCD. So what is this equal to? We know that MD is equal to 0, so this does not contribute. What is MB? So MB is and LBC is 3.75. This is EI plus 2MC. So LBC is 3.75. LCD is also by EI LCD is also 3.75, but note that ICD is 2 here. Is equal to 6 into what is delta C minus delta B? So delta C is 10, delta B is 5, so it is 0.005 by LBC, which is 3.75, plus delta C minus delta D. Delta D does not settle, so it is 0.0 by 3.75. So what is the equation that we get? We get 3.75 MB plus, so this one, if you evaluate, it turns out to be, so 3.75 by 2 is 1.8. We'll get, this will be 11.25 is equal to 6 EI by 3.75 to 0.015. So what is EI? EI, it's already given as 80,000. So 6 into 80,000 into 0.015 by 3.75. Right hand side evaluates to 1920 units are kilonewtons meter. So which option does it? It is option C. Now, what is the last step? The last step is to solve the two equations. So we have two unknowns, which is MB and MC, and we have two equations in them. So one equation is 16.5 MB plus 3.75 MC is equal to minus 106.67 kilonewtons meter, and 3.75 MB plus 11.25 MC is equal to plus 1920 kilonewtons meter. Now solve these two equations. It's a 2 by 2 system. You can solve it using your calculator. You get MB is equal to 48.96 minus 48.96 kilonewton meter. So it is hogging, and MC is equal to 186.99 kilonewton meter. So this is sagging. So they are asking the absolute value of the moment at B. So it is plus 48.96, which is option A. So let's go to the last question for the day. So again, we are going to use the Clapeyron's theorem of three moments, but in this case, we have both the loading. We have a loading, that's all. So we have a loading and we don't have any support settlement. But note that we have a tricky case. That is, we have a fixed support. Now, how do we handle fixed supports? Because we cannot write a, so if we write, there's only one span. If you see, we have a problem. We have only one span. How many unknowns we have? Degree of static indeterminacy is, so the degree of static indeterminacy is you have two unknowns here. Assuming that there is no horizontal reaction, there is no horizontal force. So you have two unknowns here, one unknown here, one unknown here. So totally the degree of static indeterminacy is 2 minus 2, which is 2. So one span will give you only one equation, but we need two unknowns. So how do we account for it? So this is a technique. You replace the fixed support at the point A by a very short and stiff beam. Right? You know, this is what we do. So this is the point A. This is the support B. This is the point C. So here you have the point load 20 kilonewtons. Here you have the distributed loading of 10 kilonewtons per meter. Now, if this extend the span to an imaginary point A prime, so this is just some imaginary point. It's not real. So I have an imaginary hinge support at the point A prime. But what do you do? In between A prime and A, the span is filled by a rigid beam. So this is a very rigid, short beam. So it's like I is equal to 0. Sorry, I is equal to infinity for this. I A prime A is like very large. It is almost infinity, which means this beam at this point, this beam cannot bend at all. It will remain stiff under any applied loading. This cannot bend. And if it cannot bend, what does it mean? If it cannot bend, here the rotation is 0. And if the rotation is 0, it mimics the fixed support. So that is the technique we use to handle fixed supports by the Clapeyron's theorem of 3 moments. Now let us see how to solve this problem. Now we have how many spans? We have 2 spans. So we have one equation for the span A prime AB and another equation for the span ABC. So I have 2 equations and 2 unknowns. So we can solve for this. Now, how do we? So the rest is direct. The rest is quite straightforward. So for the span, let us write down the. So what is L A prime A? You can take it as any small value. Say it is just some L, which is very small. Very, very small. And what is LAB? It is 3 meters. What is LBC? It is 4 meters. What is IA prime A? That tends to infinity. IAB is equal to IBC is equal to I. E can be taken as the E is constant. Apart from that, we know that MC is equal to 0. The moment at the point C is equal to 0. And the moment at the point A prime is equal to 0 because it is hinge support. What else do we know about this problem? There is no support settlement and there are applied loadings. So first, let us consider the span AB. Let us consider the span AB. So it is something like this. So what is the primary structure? In the primary structure, it consists of a sequence of simply supported beams. So the span AB is nothing but this. Something like this. And you have a uniformly distributed loading of 10 kilonewtons per meter. So what is the bending moment diagram for this? It is something like this. It's quadratic. It's 10x minus x, 10x, 10. So you know it is W L into L minus x by 2. Wx into L minus x by 2. This is the bending moment diagram. So the maximum occurs at the middle. What it is WL square by 8. So here it is 10 into what is the length? It is 3 square. So 10 into 3 square by 8. The value is here it is 10 into 3 square. And it is positive. Right? So that is simple. This is for the span AB. In span A prime, nothing. So span A prime A, everything is 0. Moments are 0. So now what is that we need for that? We need AAB. AAB is nothing but the area under the bending moment diagram in span AB. So you know that if it's a parabolic bending moment diagram, the area is 2/3 of that of a rectangle. So it is 2 by 3 times 10 into 3 squared by 8. So this is the height of the rectangle and the length of the rectangle is 3. So, and where is the centroid of this with respect to the point A? So this is the point A, this is the point B. With respect to A, the centroid XAB, this is kilonewton meter square. The centroid XAB is at L by 2, which is at 3 by 2 meters. So the quantity XAB, AAB is, so 3 by 2, 2 by 3 gets cancelled. You get 10 into 3 cubed by 8, which is nothing but 67 minus 67.5 kilonewton meter cube. Now let us write down the moment, 3-moment equation for the span A prime A B. So for the span A prime A B, we have M A prime L A prime A by E A prime A I A prime A plus 2M A to L A prime A by E A prime A I A prime A plus LAB by EAB IAB plus MB into LAB by EAB IAB is equal to minus 6 times area under the bending moment diagram for the span A prime A x A prime A by L A prime A. Just a minute. So this XAB, it is not 67. This one is, let me find out. It is 3 cube is 27, 27 by 8. So it is 270 by 8. It is something went wrong here. So it is area under the bending moment diagram is WL square by 8, 3 square, 2 by 3, 3 by 2 gets cancelled. So 10 into 3 cube. So this is 33.75. So this value is minus, not minus, this is plus 33.75 kilonewton meter square meter cube. EA prime A, IA prime A plus A AB X AB by LAB EAB IAB. So what is that we get? We know that MA prime is 0 and also IA prime A is infinity. So this term vanishes. So this term vanishes. Here also IA prime A is infinity. So 1 by infinity becomes 0. So this term vanishes. So what you get is, what is LAB? It is 3. So 2 into 3 is 6 MA. And EA is constant. So except for the virtual span, right? Except for the imaginary span, for the real span, it's all constant. So EI is constant. I can take MA by EI plus MB into LB. So what is LAB? LAB is 3 meters. So it is 3 MB by EI is equal to minus 6 into, again, EA prime, IA prime. This is infinite. So this is you have an infinity in the denominator. So this is 0. And AAB XAB is 33.75. What is LAB? LAB is 3 and EA is just EI. So 33.75 by 3 is something like 11.25. 11.25 into 6 is minus 67.5 by EI. So you can cancel out EI everywhere. So the equation that you get is 6 MA plus 3 MB is equal to minus 67.5 kilonewtons meter. So this is one equation. The first equation is, so it is option C, 6 MA plus 3 MB is minus 67.5. Now again, let me copy this so that let's go to the next problem. Yeah, next part of the same problem. Apply the moment theorem to span ABC. So in span ABC, what do we have? In span ABC, we have MA LAB by EAB IAB plus 2MB LAB by EAB IAB plus LBC by EBC IBC plus MC LBC by EBC IBC is equal to minus 6 times AAB XAB by LAB EAB IAB plus ABC XBC by LBC EBC IBC. So the left hand everywhere. So EAB IAB is equal to EBC IBC is equal to EI. So you can simply write it as MA LAB plus 2MB into LAB plus LBC. What is MC? We have MC is equal to 0 because it is a hinged support. So this is 0 is equal to minus 6 times. We already have this value. What is AAB XAB by 30 LAB? It is 33.75 by 3 plus we need to find this quantity. Let us find it. How do we do it? So consider the span BC. What do we have? Let's go back to the problem. So in span BC, you have a midpoint load of 20 kilonewtons. So span BC. Span BC, you have something like this. And you have a midpoint load of 20 kilonewtons. Span is 4 meters. So what is the bending moment diagram? Very simple. So you'll get 10, which means the maximum bending moment is 20 kilonewtons meter. This is 20 kilonewton meter. So what is the area under the bending moment? ABC. So this is positive. So it is half into 4 into 20. It's 40 kilonewton meter. What is XPC? XPC is the length to the midspan. So it is 2 meters. So what is ABC, XBC by LBC, EI? So EBC, IBC. It is 40 into 2 by 4 into EI. It is nothing but 20 by EI. So the value you get here will be 20 by EI are cancelled out everywhere, so it's just 20 by 1. So this is just so this we have already determined 33.75 into 2 is 67.5, and 67.5 plus 120 20 into 6 is 120, so it is 187.5. Just plug in the values. In one step you get the answer as what is LAB? LAB is 3 MA. And what is LAB is 3, LBC is 4, so 7 plus 14 MB is equal to, so 67.5 plus 120, which is minus 187.5 kilonewton meter. So the answer is option C. Now that we have the two equations for the two unknowns, MA and MB, the last step is to solve them. So how to solve them? So the system of equations is 6 MA plus 3 MB is equal to minus 67.5 and 3 MA plus 14 MB is equal to minus 187.5 kilometers meter. So if you solve the system of 2 by 2 equations, you get MA is equal to minus 5.1 kilonewton meter. So since you have a minus sign, it is hogging, and MB is minus 12.3 kilometer. Again, it is hogging. So the correct answer is option A. So that brings us to the end of today's session. Let me stop sharing. So I hope this session was helpful. I hope this would help you solve the assignment problems. So basically, you have to apply the method of consistent deformation. So after identifying the redundant reactions, you have to apply the method of consistent deformations, and the rest is all just integration and plugging in the values. So thank you all for attending. Let me stop the recording and close the session. So thank you, everyone.